A geometric sequence has an initial value and a subsequent sequence of values based on a common ratio. Now, the common ratio is going to appear to be the changing of the sequence by a factor, by multiplying or dividing by a constant ratio, and that's what the ratio is going to be, multiplication or division. Whereas before, when we did arithmetic sequences, it was the change or the common difference of adding or subtracting in the sequence. And it's going to be modeled very similar to a exponential function, where an exponential function was listed or identified, could be identified as y equals a times b to the x power, and a is your initial value, b is going to be your growth, and then x is going to be the number of time over time. Well, in a geometric sequence, we are going to, b is going to be equivalent to my common ratio, and the common ratio is going to be what, of course, those terms are changing by. In an exponential function, b is what my terms are changing by. A is going to be the initial value, and in a geometric sequence, that initial value is going to be your first term, which is a1, where you start. So as we get through this, being able to identify the initial value and the common ratio, it reads, which of the following are geometric sequences, and if the sequence is not geometric, is it arithmetic? Well, we know from before that arithmetic sequences have a common difference. And arithmetic sequences would be D, we take one term and we subtract the previous term from it to see if there's a common difference. So if we look here on B, we have 6 minus 3, which is 3. And then if we took any of the other terms and we said 15 minus 12 is 3. So it looks like I am adding 3 each time I go to the next term. So that would be arithmetic. That is not, in this case, geometric. So here, if I look at C, if I take, in order to find a common ratio, I take one term and I divide it by the previous term, and that is my common ratio. So if I take 7 divided by 4, not sure what that is, 1.75. And then if I take 11 divided by 7, that quite honestly is not 1.75. Therefore, we don't have a common ratio. If I now say, okay, no common ratio, let's look for a common difference, I would take 7, one term minus the previous term, and I get 3. And then I just pick any other term, and I get 16 minus 11, and that is going to give me 5. Okay, it doesn't look like I have a common difference either, so this one falls under the neither category. And up until we start working with, up until about Algebra 2, the only functions that we are really going to work with in this case are sequences, will be our geometric or our linear or arithmetic sequences until then. So, okay, so now if we're looking for an R, remember we're taking one term and dividing it by the previous term. So if I take 6 and I divide it by the number before it, that is going to give me a 2. If I take 12 and divide it by the number before it, that is going to give me 2. Therefore, it looks like I am going to find a common ratio, and that common ratio is 2, or that is what R equals. And then this next sequence, I can look at this and I can say, well, it looks like I am multiplying by 1/3, which is my common ratio, then is 1/3. But if you can't recognize that, we'll just go ahead and take one term and divide it by the previous term, and then of course that is 1/9 times 3 over 1, which is going to be equal to 3 over 9, or 1/3. And then you can pick any other term, and I can say that I have 1 over 27 divided by 1 over 9, which is going to be 1 over 27 times 9 over 1, which is going to again be 1/3. Therefore, I do have a geometric sequence, and my common ratio is 1/3. Okay, so that's stepping into identifying a geometric sequence. So if we move forward and we start looking at finding the recursive and explicit formulas. All right, so my explicit formula, and I put this on all our notes. The explicit formula is going to be an, which is some future number, some future term number, is going to be equal to a1 times my common ratio raised to the n minus 1 power. That's my explicit formula, and explicit formulas, if you remember, allow you to go to an exact location within a sequence. Now, on the other hand, a recursive formula is going to be a little bit different. Of course, these both will get me everything that I need to know in a sequence, but the recursive formula depends on the previous number in order to find the next number. So an is going to be a n minus 1, so the number before n times, goodness, that was completely wrong, times r, and that is how I find the sequence number and a recursive formula. But we also have to identify that a1 is going to be some value, because you have to know what a1 is, because you have to know where your sequence starts. So looking at those equations, we have an equals a1 times rn minus 1. That's my explicit. And then we have the recursive, and then it's going to be an equals a to the n minus 1 times r, and of course my a1 value is something. Now, the only thing that you have to change in these formulas is going to be your a1 and your r value. Everything else will remain part of the equation. So finding my r value here, first of all, let's see, I have r is going to be equal to 4 divided by 2, which is 2. And if I check it again, r is equal to 8 divided by 4, which is 2. So we know that my r is going to be 2. And then a1. a1 is going to be that first term. And in case you've forgotten, that's my first term. Then I have a2, my second term, a3, my third term, a4, and so forth. So a1 is going to be 2. So when I fill in my explicit formula, I'm going to have an is equal to some number times r raised to the n minus 1. And my r value is 2. And my a1 value is 2. And then there's my explicit formula. And then my recursive formula, I have an is equal to an minus 1 times my r, and then a1 equals. And again, my r value is going to be 2, and my a1 value is going to be 2. And there you have it, these two equations, functions, sequences, will identify what we need to know within our sequence based on its characteristics of r and a1. Okay, so continuing on, what we want to do is, well, let's just look real quick, and let's see in B here. Hopefully you can quickly see that your r value is going to be equal to 1/2. So I have 20 divided by the number before it. It's going to give me 1/2. And I also have 20, sorry, it doesn't do me any good to do the same one twice. 10 divided by the number before it, which is going to give me 1/2. And then a1 is going to be equal to 40. So when I go to replace all the information, and I'm just doing this for easy fill in, and let's see here, so we said that my r value is going to be 1/2, and then my a1 is going to be 40. And there you have it. That's how we would work out these formulas. And now what that allows me to do is I can pick any a value, any term number. For example, we know this is term 1, 2, 3, 4. So if I wanted to go to the 7th term, well, I could just go to A7 using the explicit formula, which is that one. A7 equals 40 times 1/2 to the 7 minus 1, and that is going to be A7 is equal to 40 times 1/2 to the 6th. All right, and then that is going to be equal to 40 times 1 over 64, which tells me that A7 is equal to, both of those are divisible by 8 too, by the way. I can divide both of those by 8. So it turns out that A7 is going to be equal to 5 over 8. That's 5/8 is going to be my 7th term. Now, if I were to use the other formula, the recursive formula, this guy right here, well, in order to use the recursive formula, you have to have the previous number. So let's see if I just say A7, again using my recursive formula, is equal to A7 minus 1 times my R value. And of course, I need to know that A1 is equal to 40. Well, that is A7 is equal to A6 times 1/2. Well, we don't have A6, so we are going to have to follow the equation again to find out what is A6. And in order to solve for A6, we have to have A5. In order to solve for A5, we have to have A4. So that's what we're looking at here is the recursive formula allows you to find the next term based on the previous term. The explicit formula allows you to go through and do whatever term number you want. Let's see here. So keep moving on. We have R is equal to 21 divided by 7, which is 3. Or R is equal to 63 divided by 21, which is 3. So yes, we do have a common ratio of 3. And I have A1 is equal to 7. So using my formula, my explicit formula is going to be AN is equal to A1 times my ratio n raised to the n minus 1. And I have my ratio is 3. And A1 is 7. And there's our explicit formula. And then we have AN is equal to AN minus 1 times my R value. And of course, we need to identify what A1 is. And we have, again, my R value is 3, and then A1 begins at 7. And next we have, let's see here, R is equal to 30 divided by 20, and that is going to be 3/2, or 1.5. And then also we have 45 divided by 30, which is going to be, again, 3/2. And then A1 is going to be equal to 20. And then we have our formulas. In there you have our equations. You have the sequence formulas. You have AN is equal to 20 times 3/2 raised to the n minus 1 power, or AN is equal to AN A to the n minus 1 times the R value, which is 3 over 2. And I threw in some extra stuff there that don't need to be there. That was incorrect, but I do need to make sure that I am identifying. A1 is, of course, 20. And there you have it. We have broken down some explicit recursive formulas. We have identified our R value, our A1 value, and then created those formulas, which allow us to go anywhere we need to in the sequence. So remember, when dealing with geometric sequences, they are similar to our exponential functions, and of course, our explicit geometric sequence will allow us to go to any term And then our recursive formula will allow us to go to the next term in a sequence. And of course, the growth value of an explicit function, the growth value is going to be equal to your R value, and that is going to, so your B and your R are going to be the same things, and your A and your A1 are going to be your same things in your formulas. So there you have it, your geometric sequences. And now here, using these formulas to create or understand a discounted value, applying this stuff. Okay, so using these sequences, we have the example, 2 managers at a clothing sale create sequences to show the original price and the markdown prices of an item. Write a recursive formula and an explicit formula for each sequence, and then what will that price be after the 6th markdown? Okay, well, sequence number 1, let's see here. If we're looking for our R value, well, we have to take one term and divide it by the previous term, and I believe that gives me 0.85. And then if I take another term and divide it by the previous term, I also get 0.85. So my R value is going to be 0.85, and then my A1 is going to be 60. So when I create the recursive formula, I'm going to have A1 is equal to AN minus 1 times my R value. And of course, my first term is A1 is 60. And then I'm going to have AN is equal to A1, which is 60 times 0.85 raised to the n minus 1 power. Okay, so there we go. We've created our recursive and explicit formulas based on the sequence. And now it wants us to, what is the item after the 6th markdown? So we're just going to plug in to find the 6th markdown. But we can't just say, hey, n is equal to 6, because that's actually not going to be the first markdown. This right here, $60 is my first term, and that's the starting value. That's A1. So I don't have a markdown there. I have a markdown. My first markdown starts at term 2. So I need to do 6 terms plus term 1. So I'm actually looking for A7. I need to find A7 because that will indicate the 6th markdown. So I just substitute into any of these equations. Doesn't matter which one. So I'm going to go ahead and use the explicit right here. And I have A7, because wherever I have an n, I'm going to replace it with 7, is 60 times 0.85 raised to the 7 minus 1, or the 6th power. Okay, so, and that is going to then be equal to, when I plug it into the calculator, $22.63. So that's the discount price with the first sequence in the first manager. Now the second manager, if I take 52 and I divide it by 60, I'm not sure what that's going to be. Or if I take 44 and I divide it by 52. Because those turn out that those aren't the same values, and they are therefore not a geometric sequence. But what they do prove to be is arithmetic. Because look, I happen to be minusing 8 each time. And we said if we subtract or add, then it is a arithmetic sequence. If we multiply or divide, then it is a geometric sequence. Okay, so if it's arithmetic, then we know then we have AN is going to be equal to A1, which is $60, plus n minus 1 times my common difference, which is negative 8. And if we simplify that, we can do some distribution, and that would be negative 8n times, or I'm sorry, negative 8n minus 1 times negative 8, which is negative 8. So we have 60 plus 8 is going to be 68 minus 8n is what a to the n power is going to be equal to. And then the recursive formula would be an, I believe, is going to be equal to an minus 1 times d. And of course, a1 is going to be some value. And those should be the two formulas that you're looking for here. And it turns out when you go ahead and you plug in right here and we go and we find a 7, looks like we're going to have 68 minus 8 times 7, which is 68 minus 56, and therefore we have a7 is now going to be equal to $12. So those are how the two discounts work, one with explicit or math multiplication and division, the other one with addition and subtraction. Okay, as I was saying, geometric sequences and exponential functions are related in the sense that a geometric sequence, we have the initial value multiplied times the ratio over a sequence setting, a sequence term, where in geometric sequences geometric functions, we have the initial value times my growth rate raised to some value over time, and those two are the same thing. Basically, b and r represent the same values, the growth value or the rate of change, the growth value or the common ratio, and then a is equal to a1, the first term, the initial starting value. So when we look at this equation, we can say that the geometric sequence has an initial value of 2. Well, that tells me a is equal to 2, and a common ratio of 3. Okay, well, if r is 3, then also b is going to be 3. And it asked me to write a function to represent the sequence and then graph that function. Well, if a is 2, I have y is equal to 2 times my growth, which is common ratio or growth is 3, and that's going to be raised to the x minus 1 power. And there is a formula for my sequence, and if I'm going to graph that, pretty simple. A lot of students asking me, what are you going to do? I'm just going to plug numbers in and take them out for x and y. And then, of course, we have in here 2 times 3 to the x minus 1 power, which would give me, substituting in 0, I'd have 2 times 3 to the 0 minus 1. And then I have 2 times 3 raised to the 1 minus 1, which is 2 times 3 raised to the 0. Then 2 is going to be 2 times 3 raised to the 2 minus 1 power, which is going to be 6 to the first. And I'll just go ahead and say 6 to the first. This answer right here is going to be 4 times 1, because any exponent to 1 is going to be, any number to the exponent of 0 is going to be 1, so that would be 2 times 1, and that is going to be simply 2. And then last but not least, 3, so I'm going to have 2 times 3 to the third minus 1, which is going to be 2 times 3 to the second. So that is going to be 2 times 18, which is 36. So we have 36, we have 16, we have 2, and negative 1. So there we have it. We have some points that we can go ahead and graph. Okay, so I have my x and my y, and I'll just go 1, 2, 3, 4, and I'm not sure what I need to graph to. 36, 2, 4, 6, 8, 10, 18. So there's 9. Let's see here if I go by 2s. I wonder if that'll get me there. 2, 4, 6, 8, 10, 12, 14, 16, 18. Close enough. So I'm going to start with my points, and I have 0, -1, so that would be right there. I have 1, 2, which would be 1, 2, and 2, I'm going to have 6. All right, so let's see. Let me check something here. All right, so I was able to find a mistake. This first one, when we have 0, that should be 2 to the third power, because 3 to the -1 would become a 1 over 3 with a positive 1. So therefore, the fraction here is actually going to be 2/3, not to be mistaken with what we had before. So the first term, 0, is 2/3. 1 is going to be 2. 2 is going to be 6. And then finally 3 is going to be 36. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So somewhere way up there. So let's looking here. It just says graph the function, and we've graphed what we can, and making sure that there's no discrepancies or things that we left out. But you could see here, if you needed to, that is forming a exponential line. So what do we need to know here? Exponential functions are very closely linked to geometric sequences, and the ratio is equal to your b value, your growth value, which would appear in your y equals ax raised to the b power. So just keeping that in mind, there is a very solid link between exponential functions and geometric sequences.